Nuclear chemistry is there's not a whole lot of information we have to cover in this unit, and so it kind of gets smushed into Unit 4. So basically, I'm just going to go over a couple definitions, what it means to balance a nuclear equation, and then the concept of something called half-life. So first, we have what's called a fission reaction. Fission reactions are what happen when large atoms split into lighter ones. And that'll make sense when I give you an example. There's a lot of energy associated with a fission reaction. We can harness this energy. This is actually what we use in nuclear power plants. So this is the type of reaction that takes place in a nuclear power plant. So if we think of an atom of uranium with a mass number of 238, and remember that is protons plus neutrons on the top, and the atomic number of uranium is 92, and I get that from the periodic table if it is not provided. This thing is radioactive, and so I can force it to split into smaller atoms, like an atom of Te with a mass number of 128, and it has an atomic number of 52. And another atom of Zr with a mass number of 110, an atomic number of 40. So this is something that's large and heavy, and then I can manipulate it and cause it to undergo a fission reaction, in which case we end up with two smaller atoms. These two are lighter, and there is a lot of energy that gets released when we break these two things into individual atoms there. The opposite of fission is what we call fusion. So a fusion reaction would be taking two lighter atoms and joining them together. To make something heavier. And so we don't actually do this on planet Earth because it's very, very energetic, much more energetic than a fission reaction, and we have yet to develop the science to where we can control this, but this is what happens in the sun. So fusion reactions are what occur in the sun. And so an example of that would be like if I take this atom of beryllium and I ram it really hard into an atom of carbon, and what gets produced is an atom of neon. So two smaller things being slammed together to produce this atom of neon, which is, there's a lot of energy associated with that. When we talk about balancing nuclear equations, it's pretty easy. If you look at this as if it's a math problem, and where the arrow is, if you kind of treat that like an equal sign, the numbers on the top have to add up to equal each other on both sides of that equal sign. So 9 plus 12 equals 21, and then 4 plus 6 equals 10. So if I gave you something like this, and instead of telling you what this was, I just left a blank, it's pretty easy to figure out. And I'm going to do a couple examples of those with you. Then we also learned about nuclear decay. So nuclear decay occurs when a radioactive atom decays, or it breaks apart and it releases certain kinds of particles. And there's a couple different types of decay that you have to know about. The first is called alpha decay, and alpha has like a funny Greek letter, which you'll see used on the UT Quest. So alpha decay, the way we know alpha decay happens is there's the release of a helium nucleus, which looks like this. So if we have a reaction where we see this thing in the balanced equation, then we know we have alpha decay. That's how we identify it. So what that looks like is something like this. Here's an example. If this atom undergoes alpha decay, it produces that guy. That's what identifies it as being alpha. And then if I fill in the blank, 4 plus a number has to equal 245. Well, that number is 241. 2 plus a number has to equal 93. That number is 91. And then I just check the periodic table against element 91 to find that this is Pa. That's what goes there. So that is alpha. Then we have a type of decay called beta decay. And that's when we see the release of an electron. And the way we represent the electron is by doing a 0, a -1, and an E, because this -1 actually causes our number of protons to change. And the reason for that is this electron that gets released actually comes from a neutron. So if this is a neutron, it would split into a proton and an electron. The proton stays in the atom and the electron flies off. And so we have to increase our number of protons because we're gaining a proton, but the electron is being lost. And so that's why we write it like that. So an example of beta decay in action would be if I have this atom of iron and it goes through beta decay. And so then I just balance it the same way I would have before. 0 plus what equals 50? Well, 50, there's no change there. -1 plus what equals 26? 27. So be very careful about that. This -1 causes 27 to decrease to 26. And then again, I just check the periodic table to find element 27, and that is CO. That's how I identify beta decay. The funny symbol for that looks like that guy. So if you see that on UT Quest, that's what beta means. There's also something called gamma decay. And gamma decay is really just a release of energy, of pure energy. And so we don't actually see a change in element. So if I got something undergoing gamma decay, the way I have to indicate that, because there's no change in mass, there's no change in the number of particles. So the stuff on the right side of the arrow looks the same as the stuff on the left side of the arrow. But I put a little asterisk up there to show that's how I indicate something's undergone gamma decay. And gamma is like a weird looking Y thing for its letter. There's a couple others on this assignment that I'm going to ask you to do. So here in this first section, it says to balance these according to an alpha particle being emitted, which means every single one of these releases an alpha particle, and then you balance it accordingly. So we're looking for the emission of an alpha particle. Here, we're balancing under beta decay. So every single one of these is releasing that beta particle, and then you balance accordingly. This one is a little bit different. This one is called electron capture. So here we see the electron being released on the right side of the arrow. Electron capture is kind of like the opposite of that. The electron is on the left side of the arrow, so every one of these blanks gets that electron, and then you still balance it like you normally would. So 106 plus 0 is 106, 47 plus -1 is 46, and then we check the periodic table to identify 46 as being element PD. And then positron emission is where we emit something called a positron. And so when I say emit, that means it's on the right side of the arrow. And it's sort of like an electron, but instead of an electron, it's something called a positron. So it's 0, and instead of a -1, it's a +1, and then we put a little p to represent the positron. And then, of course, we balance as normal. So 0 plus some number equals 116. And then 1 plus a number equals 50. So this is 49 here. And then again, we check our periodic table to find that is element In. And then down here, you just fill in the blank with the balancing, and it fits into, each one of these fit into one of these 4 categories. So when you fill in the blank, it either looks like this with an alpha particle, it looks like this with an electron on the right side of the arrow, it will look like this with an electron on the left side of the arrow, or it'll look like this with a positron on the right side of the arrow, and that's how you can identify what type it is, what category. So that is the types of decay in nuclear reactions. And so lastly, let's just talk about half-life. This concept of half-life. All half-life means is the amount of time it takes for something to decay by half. So for example, if I say I have a substance and I have 500 grams of my substance and the half-life is 5 days, and then I say how much remains after, I don't know, let's do 20 days. How much remains after 20 days? So if I think about this, if each half-life takes 5 days and I want to know how much is left after 20 days, that means it undergoes what we call 4 half-lives. So if I start with 500 grams, 5 days later, I'm going to have half as much, so 250. And then 5 days after that, this 250 will have decayed by half to 125. 5 more days pass. That 125 decays, what is half of 125? to 62.5. And then we undergo one more half-life because we want to go a full 20 days. So then half of 62.5 is 31.25. So that answers the question. That is how much is left after 20 days if they're, if each half-life is 5 days long. Okay, so you have the little balancing assignment you can be working on. So balancing the nuclear decay. And then there's also a UT Quest. It's 4.1. It has some nuclear in it, but it also has some light problems in it. And I'm going to do a different video for that. So if you want to start tackling the UT Quest 4.1, then only work on the questions that pertain to nuclear, and then don't do the ones about light until you watch the second video. Thank you very much.
Does 85%